Lecture 22 does not cover a section from the text. At the end of today's lecture, you should be able to derive the relationship for relative pressure and relative volume for isentropic processes for ideal gases. Now, recall our change of entropy for an ideal gas undergoing an isentropic process. ds is going to be equal to 0. And we can express this as our standard entropy at state 2 less our standard entropy at state 1 minus r times the natural log of P2 per P1. Say we know the temperature at state 1 and our pressures at state 1 and state 2. Thus, we could solve for a standard entropy at state 2, such that S0 of T2 would be equal to S0 of T1 plus r times the natural log of P2 per P1. Since T1 is known, it follows that our standard entropy could be found via interpolation from our steam tables. Then S0 of T2 could be calculated, and then T2 could be found via interpolation from that known value. Alternatively, rearranging our first expression in terms of pressure, we could solve for pressure at state 2 being equal to pressure at state 1 times the exponential of our standard entropy at state 2 less that at state 1 per our gas constant R. Or if we re-express this in terms of the ratio of pressures, P2 per P1 would be equal to exponential of our standard entropy at state 2 per R per our standard entropy at state 1 per R. The numerator and denominator within the exponential are solely functions of temperature. That is, we had standard entropy at states 2 and 1. Our gas constant R was a constant. And each quantity is termed relative pressure, P sub R. Now, P sub R should not be confused with our reduced pressure that we use to verify the applicability of our ideal gas law. In this definition, we can say P2 per P1 would be equal to our relative pressure at state 2 per our relative pressure at state 1. This formulation is only valid for isentropic processes, and these relative pressure values are provided in table A72. We can also derive a relationship between our specific volume and temperature. Recall for an ideal gas, the ratio of our specific volumes between states 1 and state 2, nu2 per nu1, would be equal to r T2 per P2 times P1 per RT1. Now, since states 1 and state 2 have the same entropy, since this is an isentropic process, nu2 per nu1 can be expressed as RT2 per our relative pressure evaluated at state 2 times our relative pressure at state 1 per RT1. The ratio of our gas constant times our temperature per relative pressure is defined as our relative volume, nu sub r, which is expressed as nu2 per nu1 would be equal to nu r2 per nu r1. Now, what's nice is these two relations can be used in conjunction with our previous expressions, namely our expression relating temperature and pressure, pressure and volume, and temperature and volume based upon K, our ratio of our constant pressure to constant volume specific heat. The benefit of using our relative pressure and relative volume is that it uses standard entropy, which takes into account the temperature dependence of these properties, unlike where we used our isentropic index, which uses K, which is taken at standard temperature and standard pressure. Thus, we'd expect a more accurate solution. And to illustrate this, let's look at an example. A rigid, well-insulated tank initially containing 5 kilograms of air at a pressure of 500 kPa and at a temperature of 500 degrees Kelvin develops a leak, and the air slowly escapes until the pressure within the tank reaches atmospheric. We want to determine the total amount of mass remaining in the tank at its final temperature. First, to begin, we are going to write out our state variables. At state 1, we have a mass of 5 kilograms, a pressure of 500 kPa, and a temperature of 500 Kelvin. At state 2, we know our pressure has reached 100 kPa. It would be wrong to assume that our temperature is equal to atmospheric. Now, the mass and temperature at state 2 are both unknown. We can solve for a mass at state 2 via the ideal gas law. M2 is equal to P2 V2 per RT2. Or if we express this in terms of volume, V2 is equal to our mass at state 2 times our gas constant times our temperature at state 2 per our pressure at state 2. The mass at state 1 is known, and similarly, we can solve for a volume at state 1. The benefit of doing this is we recognize this problem as a constant volume process. That is, if we say our volume at state 1 is equal to our volume at state 2, we can say M2 R2 T2 per P2 is equal to M1 R1 T1 per P1. Or our mass at state 2 is equal to our mass at state 1 times the quantity or pressure at state 2 per that at state 1 times the quantity or temperature at state 1 per that at state 2. We know our pressures at state 1 and 2 and our temperature at state 1. All we have to do is find our final temperature. The problem statement has keywords, well insulated and slowly escapes, so we can assume this is an isentropic process. That is, our change of entropy is going to be equal to 0. That means we can use our relative pressure formulation. P2 per P1 is equal to our relative pressure at state 2 per relative pressure at state 1. Or our relative pressure at state 2 is equal to P2 per P1 times our relative pressure at state 1. Now if we go to table A72, our relative pressure at state 1 has a value of 6.7663, and this is dimensionless. Our pressure at state 2 is 100 kPa, and our pressure at state 1 is 500 kPa. Thus, if we populate our equation, solve for a relative pressure at state 2, we find the value to be 1.35326. And if we look, this pressure lies between 300 and 320 Kelvin. At 300 Kelvin, we have a relative pressure of 1.1146, and at 320 Kelvin, we have a relative pressure of 1.3972. Thus, we are going to exist in between these values. If we interpolate, we find our temperature at state 2 to be 316.89 Kelvin. Thus, the mass at state 2 is found after we insert our value for T2 into our equation. Our mass at state 2 is equal to our mass at state 1, which is 5 kilograms, times our pressure at state 2 per pressure at state 1, which is 100 kPa per 500 kPa, times our temperature at state 1 per our temperature at state 2, which is 500 Kelvin per 316.89 Kelvin, which means we have 1.578 kilograms. Alternatively, T2 could be found via the use of K, a ratio of our constant pressure, constant volume, specific heat, where T2 could be expressed as T1 times the quantity P2 per P1 to the K minus 1 per K. We know K is equal to 1.4 for air, and if we substitute in our values, we find T2 to be 315.69 Kelvin. The difference of these two answers is that K is taken at standard temperature and standard pressure. It does not reflect any variance of our material properties with respect to temperature.